Modulation is one of the most frequently used technical words in communications technology. One good example is that of your FM radio, where FM stands for frequency modulation. In this video, we are going to learn the basics of modulation techniques and see how they are applied in modern cellular and communications technology. Frequency and wavelength of a wave are inversely connected. Humans have the capability to hear sound frequency from 20 Hz to 20 kHz, but if a radio tower transmits electromagnetic waves of the same frequency, the size of the antennas required will be really high. In the antenna video we have already seen that the size of the antenna is proportional to the wavelength. If we had transmitted the electromagnetic wave in the same frequency of sound, the antenna size required would have been in the range of kilometers. This is why we need modulation. Before the electromagnetic waves are transmitted, they should be modulated to a high-frequency signal. We can understand the way we modulate the signals with a simple analogy. Try throwing a piece of paper. It won't go far. Now tie it to a stone and throw it again. The second method is obviously more efficient than the first one. This is exactly how we do modulation. In place of a stone, modulation uses a high-frequency signal known as a carrier signal. As we know, any signal has three basic properties: amplitude, frequency, and phase. In the modulation process, one of the properties of the carrier signal is varied in accordance with the message signal. For example, the frequency of the carrier signal is varied according to the amplitude of the message signal. This technique is known as frequency modulation. Please note that the frequency of a carrier signal is always high, which means the modulated signal is also of high frequency and energy. The value of the original signal can be easily retrieved from the frequency of the modulated signal. In the same way, we can also achieve amplitude modulation. Here, the amplitude of the carrier signal is varied based on the value of the message signal. The modulation techniques we have discussed so far have all been analog types. However, they are already obsolete. Analog modulation is susceptible to noise, which degrades the quality of signals. And moreover, in today's electronic instruments, all operations are carried out in digital form, where the digital signals are either a 1 or a 0. So, let's discuss the digital modulation techniques that are currently used. More specifically, let's see how the digital bit flow is converted to an electromagnetic wave. The first digital technique is amplitude shift keying. Here, based on the digital pulses, the amplitude of the carrier signal is adjusted. High amplitude relates to 1 and low amplitude relates to 0. The next technique is called frequency shift keying. Here, based on the value of digital pulses, the frequency of the carrier signal is adjusted. In this case, high frequency relates to 1 and low frequency relates to 0. The third technique is phase shift keying. Here, the phase of the carrier signal is changed by 180 degrees when the digital pulse moves from 1 to 0 or 0 to 1. Telecommunications technology is all about increasing data transfer speed and efficiency. But if you use any of the digital modulation techniques explained previously, you wouldn't get a high data transfer speed. However, there is a technique in physics which, if you use it, means you can practically send up to 6 bits of information as a single electromagnetic wave. This technique is known as quadrature amplitude modulation. To understand QAM in an easy way, let's take two analog signals. The beauty of QAM is that you can modulate these two different signals as a single signal and then transmit it. Then at the receiver end, you will be able to separate out the original signals, thereby saving bandwidth. Let's see how this modulation is done. In QAM, the first signal is amplitude modulated using a carrier wave as shown. The second signal is also amplitude modulated with a carrier wave of the same frequency and amplitude, but after giving the carrier signal a 90-degree phase shift. Now, these two modulated signals are mixed together and form a single signal. We call it a multiplexed signal. The interesting thing is that on the receiver side, we can easily separate out the original signals from the multiplexed signal. In the case of digital QAM, a similar approach is used. Here, instead of analog signals, different combinations of bits are added together to produce a multiplexed signal. Let's see how a 16 QAM works. If you are familiar with digital technology, you know that any form of data is just a collection of ones and zeros. In 16 QAM, we can pack 4 bits together and send it as a single electromagnetic wave. Based on the values of the 4 bits, this output will have different phase angles and amplitude. This means the phase angle and amplitude of the multiplexed signal can completely represent 4 bits of data. In 16 QAM, such 16-bit values can be represented by adjusting the phase and amplitude of the multiplexed signal. And this single multiplexed signal is then used for the transmission. You can see how the different amplitude and phase electromagnetic signals represent various 4 bits of data. Using a similar technique to that used in analog modulation, here the amplitude-modulated signals are also mixed together, and finally, a single output is produced. As we have seen in this modulation, 2 carrier signals that are out of phase by 90 degrees are used. Hence the word quadrature is used to refer to this technique. If, instead of QAM, we had used a normal modulation technique to send bits of data, we would have used 4 electromagnetic signals. Thus, 16 QAM increases the data transfer speed by 4 times. Scientists have even achieved 64 QAM, which is used in 4G communications. 64 QAM uses 6 bits of data at a time, thus making the data transfer speed 6 times faster compared to a normal modulation technique. The modulation techniques are not restricted to only cellular communication and FM radio, but also have applications in television broadcasting, Wi-Fi, optical fibers, etc. We hope this video has given you a clear understanding about the concepts of modulation. Thank you.